Hello everyone, my name is Pratyush and I welcome you all to another video on my IBM Capstone for the Advanced Data Science Specialization, which is titled as Forecasting the Highest Stock Price of RICs Over Time with Advanced Machine Learning. And I hope you all had a chance to check out my previous video in which I demonstrated my final end user business data product, which is a web application that takes an RIC ticker as input, and on clicking the submit button it displays the forecasts of its daily highest price for the next 6 months until March 2024 using the chart.js visualization. If you haven't done so, please go ahead and check that out and share your reviews. And coming back to this video, here I would like to go over the inner workings of the two models that I have built, namely the Random Forest and the LSTM. I would like to show you what the steps were involved in building these models, how I created the feature vectors, how I performed hyperparameter tuning, defining my training and testing data, and for the LSTM, how I created the lag sequences, defining the output layers, the idea behind it, and using early stopping and all those details. I'll be going over my Jupyter notebook, and just to let you know, all the GitHub gists to my Jupyter notebooks, they have been mentioned in the description of this video. Please feel free to go ahead and check them out. So coming back, so this is the model training notebook, and before I go, I would like to show you what my transformed data set looks like. So after the data set goes through the EDA and the ETL phases, this is what it looks like. So this instrument is basically the RIC name. Instrument is another name for RIC ticker. So you could see if I take this particular row, you have a given RIC for a given year, the given month. I have the average highest price, opening price, closing price, the daily return, which I told you is a calculated feature defined as the difference between the opening and closing price, the average volume, the total volume, and if you also remember, volume was not an important feature, so it's not relevant to our feature set, but yet it was used in calculating those. So the column exists in our transformed data frame. And I'm using PySpark as my underlying data structure because a major learning curve for this course was making our data analysis and manipulation compliant with parallel processing. So I wanted my data frames, the data analysis that I'm doing on them, to be scalable if I were to run them on multiple compute nodes. So that's the reason why I chose PySpark data frames as my underlying data structure. Yes, you can also use pandas, but keeping the learning curve and the end goals in mind, I've used PySpark. So coming back, so first I define a model set, hashing out all the relevant columns that will be used for building the models. And first I implement the random forest regressor. So the first three steps, namely creating the feature vectors, an optional scaling of those feature vectors, and defining the training and the test data. These three steps are common for both of the models. Like regardless of them being from different stacks, these are the fundamental steps. We'll do them for the random forest as well as the LSTM neural network. So first I create the feature vectors. If you recall, I had come up with a recommendation of two combinations for the feature set, either the opening and the closing price, or opening price and closing price along with the daily return. And I also told you that this combination was working better. I have of multiple builds of the same model with different feature vectors, but this is the main one, so I'm showcasing you, demonstrating this one. So I leverage the vector assembler from the PySpark's MLlib library, and that's also another advantage of using PySpark. It has inbuilt machine learning libraries, like having vector assembler for creating the feature vectors, scalars, and all everything. So it's a very powerful library from that perspective as well. So this is how I create the feature vector based on the opening and the closing price. The next part is scaling, and I'm using the robust scaler to scale my feature vectors if I'm supposed to do that. So usually the two most common scalars that we use are the standard and the min-max scalar, but I'm not using them because if you remember from the frequency distribution and outliers, our continuous features are not normally distributed. You can see this follows a right skewed distribution, and they're also full of outliers. Now, what standard scaler does is, is that it assumes normal distribution, whereas the min-max scaler is highly sensitive to outliers. So in our case, either of the two don't satisfy our requirements. So that's the reason why I went ahead with the third kind of scalar, which is the robust scalar. It uses the interquartile range and the median, which is exactly what I needed. So I use the robust scalar to scale my features. Of course, this is optional. You can do it and you cannot, depending upon how your feature vectors are like. In this case, you need not do it because they're pretty much on the same scale. Had there been a very big difference between them, like for example, if you take this instance, let's say the opening price was 100 and the closing price was 5 or 6 or under 10, then in that case you could have scaled them, or could have or could not have scaled them, depends upon your requirements, whatever works better. And coming back, the next part is creating the training and testing data. As I already told you, my training data is from January 2019 to September 2022 and October 2022 to September 2023 as my test data, because I wanted to include their sequential nature in my train test split. So this is how I define it. The next part is finding the hyperparameters for my random forest. So I find the hyperparameters and I found out that although this has been commented because it takes a lot of time to run, but I found out that 16 was the optimal number of trees for the for this configuration. And based on the number of trees found by the hyperparameter tuning, I retune my random forest model, set the number of trees as 16, fit on my training data, transform and predict on my test data, and I evaluate its performance using three regression testing metrics. One is the root mean square error, the mean absolute error, and the mean absolute percentage error. And if you recall, it was very high, and the differences were especially the mean absolute percentage error, and you could see there's a 428.42% error in this. And this is on the testing data. I did the same for the training data as well, and in both cases the error is very high. So although it's not overfitted, we could in a way say that the random forest on this time series data is underfitting, because overfitting is a case where any given model performs good on the training data, but its good performance does not reflect in the test data. But in this case, it's not performing good on either training and the test data. So in a way, it is underfitted. The errors are very high based on the regression testing metrics. So that's the reason why this model, the random forest regressor, is not suitable for our data set, for our time series data set to be precise. And here comes the LSTM model. This is what it addresses, the drawbacks of the regression. Now, how does it do so? First, as I told you, the initial three steps are the same. We create feature vectors, an optional scaling, defining the training and test data. So here, using a window function, I'm creating lags. So if you recall, in order to capture the temporal and seasonal nature of a time series data, what we do is we create lag sequences. Now, what are these lag sequences? So if you can see it over here, let me zoom it in a little more. Yeah. Considering this snapshot of the data frame, what I do is for every feature vector, I create 12 lag sequences. Basically, I keep shifting it down until the 12th lag. You can use 6 lags or 9 lags depending upon what you want to do. But I wanted to create 12 lags because I want to take into consideration the prices or the feature vectors for the past 12 months to predict my future time steps. So this is how the lag is created. And if you can see for the very last instance, like on which the prediction would be made, includes the feature vectors from all past 12 months. So this is where the advantage comes in. The random forest was just taking the feature vector and predicting it. It so if we were to predict for the future, the random forest will not have the feature vectors from the past month to predict the future month. But the LSTM does. It create with this lag sequence. It creates this lag sequence, 12 lag sequences, or like depending upon how much you want to create, and uses them as an input to predict or forecast for the next month. Let's go to the next step. This is the same, creating the training and the testing data. And here is where I build the LSTM model. I'm using Keras and TensorFlow. So I define my model over here. These are the basic configurations. And I create 7 output layers. If you recall, I mentioned in my previous video that depending upon how many predictions you want to make for the future, that many number of layers you'll have to define. For example, if I want to predict for the next 6 months, then my number of layers would be n plus 1. The current month or the current time step plus the upcoming 6 time steps. It's total 7 layers. And depending upon how much you want to predict, then I compile my model, and this is where I'm using the early stopping. So what this early stopping does is that it uses the callback function and tries to find the optimal number of epochs. How? So what I do is I fit it on my training data and I define the maximum number of epochs. Here I've defined as 1000. You could do for 100, but this also depends upon how many maximum epochs you want to define. Because if we go down over here, this is the kind of graph that you need. So you keep increasing the maximum number of epochs until you get an exponentially decreasing graph of something like this. So how to interpret this graph, as you can see, is the moment it stabilizes, where the training loss and the validation loss, they're both low, and they kind of at the point where they start plateauing and remaining constant, that would be the optimal number of epochs. Not even that, somewhere between them. So from this graph you can see that anywhere between 15 or 20 number of epochs, at that point our model will start overfitting. So you can choose any value between them, between 15 and 20. So what LSTM does is it, so whenever you rerun your model, your LSTM model, it automatically picks an optimal value between these two. You can also define it on your own, customize it, try to keep its nature fixed, but this also does the job for you. It'll automatically take one value between 15 or 20, and or like anywhere from this graph, and use it in your model, that many number of epochs. So for this, I would say it'll, every time when I rerun it, it'll be somewhere between 15 or 20, and based on that I predict on the test data. I come up with the predictions for the next 6 months, and finally this is where I compile all the data. I evaluate the performance, and you can see that the root mean square error over here, the mean absolute percentage error, and the mean absolute error, all these three regression testing metrics are very low compared to the random forest. And the core reason for that is these very lag sequences that the random forest is unable to capture. These lag sequences are the representations of a time series or any historical data's seasonality or temporality, as you might put it. So this is the essence of my comparison, of my use case, like why random forest or any regression model for that instance is unable to perform well on time series data, whereas a recurrent neural network like LSTM does. And so yeah, this is what I wanted to highlight in this video, and I'll quickly give a small demonstration of my data product for those who would like it. This is the final form. So what I do is I simply put an RIC ticker, click on the submit button. So it takes a little time to load. Yes, fine. So here it is. This is what the chart.js visualization is like. You can check it for the next 6 months, for November 2023, December 2023 until March 2024. You can hover over each data point and see the exact value for the is exact forecast for the daily highest stock price for the next months. You have the sector information and all of that. So yes, this is what I wanted to go over in this video. Thank you so much for staying tuned with me. Please like, share, comment on my video, share your critical reviews, check my project assets, and I would be more than happy to engage with you. Please directly reach out to me. My email and my LinkedIn, they're mentioned in the description box. I would be very happy to connect with you all. Thank you so much for staying tuned with me and hope you all have a really good day. Thank you.